right, so kicking off the conference for today, right? It's we have actually invited one of our distinguished engineer at GovTech with a deep technical expertise in simulation and animation. So I'm not sure if anyone recalls recently where there was this four-legged robot dog whose name is called Spot. Which made its Singapore debut in the Bishan Ang Mo Kio Park in May 2020 earlier during a trial with NParks. So in fact, our speaker today, Jia Yi, he leads the engineering team in GovTech, right, that develops Spot's software capabilities to carry out safe distancing tasks such as people counting, safe distancing measurements, and even detection of mask wearing. So in the first talk that we're going to invite Jia Yi on, he's going to be sharing with us some insights on GovTech's plans for digital operations smart services to be Singapore's platform for robotics and smart systems and how it fits into the Smart Nation Sensor platform. Right, Jia Yi is previously a technical director at DeepMotion. He comes with a very deep technical background, and he also used to work with Pixar for up to 10 years. So it's a really fun. Right, I'm really excited to hear what he's got to bring to us today, and also to hear about our Smart Nation plan. So without further ado, ladies and gentlemen, presenting to you our very first speaker, Jia Yi, with his talk, Bridging the Cyber Physical Worlds with Robotics and Smart Sensors.
Hello. Thank you so much for the introduction. So I'm Jia Yi. I work at GovTech as a distinguished engineer. I'm going to talk about all things robotics, machine learning, and deep learning today. We'll have a fun time, hopefully. So this is what we do in our group. We call it the Smart Nation Sensor Platform. And I'm not going to bore you with the details. So I'm going to skip through a couple of slides, like the corporate stuff, and then get right to it. But essentially, what we're doing is we're building something called the Digital Operations Smart Systems. I'll get to that in a minute. But what we do is we do three things: we sense, we contextualize, and we act. So we get real-world data, we try to analyze it, and we act on it. Essentially, what goes on is we have this stack. I'm going to go to it in more detail. So this kind of boring stuff. So let's just go to the next slide. More interesting stuff. OK, so we don't discriminate between different types of platforms. So we don't care if it's a static platform or a mobile platform. To us, it's all the same thing because they all collect data. And data allows us to act on different things. I'm going to go into, again, more detail on what we do. But we do both static sensors, for example, lamppost buildings, the SPOTON, which you might have seen in the news recently, which is an AI thermal scanner, and also, of course, robots. So what do we actually want to accomplish from all of this? We want to do remote operations. So we have something called a beyond visual line of sight robotic stack, which we've all developed in-house. We're also currently developing a fully autonomous stack as well to enable 24/7 operations. And we want to do this because we believe that mobile platforms, especially robots, are very flexible. And we're going beyond just ground robotics. We're also doing land, air, and sea. So we also have submersibles and drones. OK, so ultimately, at the core of what we do is we are heavily dependent on deep learning because, as you know, in this day and age, the world is completely unstructured, right? So we have to make sense of this nonlinear data. We have to find patterns within nonlinear data. And so one of the recent trends since 2012, since AlexNet came on board, is deep learning has become sort of a more viable approach. We have large amounts of data. We have the GPUs. We can crunch the numbers. We can construct a deep neural network, and then we backprop, right? Assuming everything's fully differentiable, we can make sense of the world. So that's what we do. OK, so now onto the more interesting stuff. Spot is a robot from Boston Dynamics, as you well all know. Now, Spot by itself is just an expensive toy, let's be honest. What we're doing in my group is we're actually developing an entire robotic stack on top of it. This is all built in-house by my really tiny team of just 5 people. We have developed currently a beyond visual line of sight control stack, which allows you to actually pilot the robot, not just Spot, but actually any robot, over 4G anywhere in Singapore. We obviously have the usual classical autonomy stuff, so we do SLAM, simultaneous localization and mapping, both vSLAM and traditional LiDAR SLAM. We are currently developing an autonomy stack, which I'll demonstrate in a few more slides. Obviously, a lot of stuff we're doing is based off deep learning, so obviously we do object segmentation, object detection, pose detection, that sort of thing. We've also deployed it for tracking, so we can make it follow people, flock control, and all that. So let's jump to something more in depth. Now, let's talk about the BVLOS, so beyond visual line of sight stack. So this was actually something that was deployed at the Chong Jia Yi Exhibition Center during the height of the COVID-19 pandemic, and we were actually using it to remotely, deliver medical supplies, crucially into the facilities. Obviously, you can imagine why. For safe, having robots do this sort of thing is much more of a safer thing than getting a personnel to go in. Now, what's really cool about this is this was all done through our custom 4G remote piloting stack. So the nurses and doctors could sit safely anywhere in the tent and then drive the robot in to deliver critical medical supplies. The second part is, of course, the safe distancing stuff at the park. Okay, so we're doing autonomous robotics, and essentially, why are we doing autonomy? Because the previous slide I showed was remote piloting, but we want to go further, right? Because having remote piloting still doesn't remove the human from the equation. We want to really do 24/7 operations, 360-degree island-wide coverage. In order to do that, we need to have a very robust autonomous stack, and it's not just autonomy for indoor environments. Autonomy in indoor environments, I'm not saying it's easy, but it's mostly a solved problem. We're interested in large-scale outdoors, unstructured autonomy. So I'm talking about autonomy in places like parks, in any of the urban, semi-urban to non-urban environments, in the forests, where you can actually move these robots in, and then you can perform various operations. That's when it gets really challenging, and that's when it gets really fun. That's a really difficult problem to solve, by the way. So we are using a combination of various techniques, obviously computer vision, SLAM, traditional stuff, but also recently a lot of deep learning based techniques for motion planning controls and point cloud reconstruction. So the first video I'm going to show you guys is, okay, let me play this. Hang on, let me play it. Okay, so the first video I'm going to show you guys is basically, this is an autonomous stack that we are currently developing. It's actually quite mature at this point. This is with traditional LiDAR SLAM approaches. So you have computer vision, LiDAR, you construct a point cloud, you do SLAM, you close the loop and you go. Obviously, it's more complicated than that. And it's actually kind of tricky to get this working in an environment like NParks. Again, this is all done through 4G and all that. It's tricky because it's an unstructured environment. This is not autonomy in an office or in a building. This is autonomy outdoors. So the point clouds you collect and everything is actually a lot noisier, and we have to develop algorithms to deal with that sort of thing. Obviously, you can employ particle filters. That's all the usual techniques you can do. But even then, I want to emphasize, it does get a bit tricky. So there are a couple of hacks that we've also employed, but in general, it's getting more and more mature. So we've actually successfully traversed autonomously environments like this using classical approaches with a lot of modification. And we're also doing increasing a lot of deep learning stuff for the segmentation part. So we actually run it through a deep neural network to actually segment out the RGB coming in, so we actually know, we can tell the dog through the classical controller which part to traverse and which part not to traverse. So it's like a hybrid approach. So that's the first technique we have already developed, and it's quite mature. Here's a second one, which I also find it really interesting. This actually just happened this, actually, let me play it again, sorry. Okay, this just happened this Tuesday. So we are developing a fully, completely deep learning based, visual autonomy based approach. This doesn't use LiDAR, GPS, or any other sensor other than onboard cameras. So with a single camera, the two other cameras are for show. Actually, the only camera that's doing the real inference is the middle camera. So with just a single camera, we can now navigate autonomously unstructured terrain as well. And this is done with deep learning, deep neural networks, of course. We have a couple of them running, and we are still developing this. But this is not just a simple end-to-end solution. This approach actually involves also conditioning on the intention, high-level intentions of where to move the dog. So we can actually train it and then let it generalize for any park environment. And we can also train it so that it's not just a fixed route, where it can actually be trained and learn to traverse a specific route that you want to plan based off high-level intentions, just like how people actually navigate real world environments. All right, so those are two techniques we're in development. I can answer more questions later along the way. Now, in addition to what I just mentioned, we can also do other kinds of autonomy type stuff as well. So One of them is we've also employed, actually developed from scratch, our own deep learning person tracking feature that's also incorporated into our robotic stack. So in this case, the robot actually can identify a person, and even if there's multiple people on the screen, it can identify a specific person. It doesn't get confused. And in real time, it will track that person through the DNN and then actuate the motors and follow the person. So this is another example of the amount of machine learning we've incorporated into our current robotics stack. As you can tell, it's heavily vision and machine learning based, but we also are dependent on more traditional and classical techniques. So we use the best of both worlds. Classical techniques, classical controllers, as you know, give you a more bigger level of guarantees, safety guarantees, right? But the more recent deep learning based approaches allow it to be more flexible and work in nonlinear environments. Okay, so that's the robotics stuff. The other thing that my group works on is obviously, we also work on payloads, sensor payloads, and one of them is called SPOTON. So this actually came out from our robotics stack. This is actually built off the DOS stack as well. So SPOTON, as you might have read in the recent news, it's an AI thermal camera. I mean, it's just a fancy name for using deep learning for thermal sensing. So this is a very affordable mobile solution that allows you to detect temperatures of people in real time, up to 10 or even more faces at once, with an accuracy of 0.3 to 0.5 degrees Celsius. And we accomplish it off just commercial off-the-shelf software. So it's actually really cheap compared to any other commercial solutions out there, which cost in excess of $10,000 to maybe $15,000. Ours is definitely, it's like way cheaper. So it's scalable, it's accurate, it's fast, it's also I think affordable, which is important in this day and age. So this is another solution that we've pushed out, and I believe it's like the first commercial licensed sort of product that's pushed out by my group. So I think we're all very happy that it happened. Okay, so we obviously add a lot of capabilities onto SPOTON. So on the right, you can see a video of it. Basically, it's running a real-time face mask detection as well. So you can put all these neural networks, you can train them, and then they can do all these kinds of interesting, useful things. So other than temperature sensing, can also tell you if a person's wearing a mask or not in real time. By the way, everything we do in our group is all done on the edge. We develop exclusively in C++, C++ 14, 17, more than C++, because we care a lot about performance. A lot of our code is actually offloaded onto the GPU with CUDA or any other kind of hardware acceleration. Okay, so let's get to some interesting code I thought I'll share. This is just, I won't have time to go through all of it, I apologize, because of limited time, but this is sort of some code that we run for maybe our face detector. As you can tell, we use modern C++ a lot in our group. We use stuff like const expression, std array, that sort of thing. Const expression, by the way, is a way to tell the compiler to build it, evaluate the expression at compile time. So it's even faster. You do evaluation in compile time, not at runtime. Anyway, so this is an example of what we're doing for our face detector. We train it with PyTorch, and then we export the model to Onyx, and then we execute it with a highly performant runtime like Onyx runtime. But there's other options as well. But again, it's all C++. And I'll just highlight a couple things I find which might be interesting for you guys, right? So the constructor is like whatever, I don't really care. Okay, so in Onyx runtime, what's interesting is because, as you know, deep neural networks are essentially graphs, right? So there's a graph optimization step involved, which you can actually set. You can set number of threads, and obviously we can enable for CUDA. The next thing you probably want to do is you actually want to get the model inputs of your deep neural network, which you do as well. This stuff's kind of boring, but I think I'll get to the more interesting stuff that we all care about. So what happens is the image comes in as an RGB, as an OpenCV RGB frame. So image comes in, and then what we do is we actually have to pre-process it, right? Because remember, an image comes in as RGB, and RGB, each R or G or B, each component, the range is from 0 to 255. So in order when we actually do deep learning, when we train a deep neural network, what we have to do normally is to normalize the inputs. This is to actually help the gradients. As we do the training, we have to help the gradients and make it train faster, because you want to make sure the inputs have sort of consistent ranges. So what we do is we actually have to normalize the input, which is what we do with this lambda norm prepare val, which is done over here. And then the next thing we want to do is we have to pack it into a one-dimensional array. The best example is actually described in this Intel documentation of paper. A tensor in a deep neural network is actually packed as a one-dimensional array for performance reasons. And obviously, when you upload it to the GPU, it processes it in a more efficient way. So the typical way is, I believe, typical way is called NCHW, which means the number of batches, because you want to batch during deep learning, the channel, RGB, the height, and the width. So this computes the offset. I think the image here describes it best. This computes the offset into the tensor. So what you do is you normalize the image, and then you compute the offsets into the tensor to encode it, and then you throw it into the tensor, right? So once you're done with that, then you just run the inference pass. Obviously you create all this stuff. Allocate the memory. That's a memory pool, by the way. Anyway, and then you run the inference. And the DNN will then give you back the result based off, assuming your weights are properly trained. So I think this part's kind of interesting. The other thing that might be interesting is we look at the phase detect code. So what we do is step back, right? So the image comes in, and then so we run inference on the DNN, and after that it gives us the result. So we extract the score, the confidence values, and the bounding box values. And then what we do is we generate the bounding box, and then we also run something called nummax suppression, which is to remove the redundant bounding boxes that are detected. So let's take a look at the generate bounding box as well. So the generate bounding box function or method, I think, is quite interesting, because what you find out is you're probably wondering, hey, the bounding box value is coming in. Why do I actually have to do this variance thing? And why do I do this exponential thing? Well, you can do a bit more reading, but basically what we do is when we actually train neural networks, it turns out it's actually easier to train to encode the bounding box values in logarithmic space for a variety of reasons. And so we have to unpack it. So we have to run an exponential to get the values back. I think this part's a bit interesting. So let's recap again. So you run one inference pass, you get the scores and the bounding box values back. You generate the bounding boxes, so you transform from logarithmic space back to your regular Cartesian space, and then you run the NMS for the nummax suppression, which is over here. So we have implemented a couple algorithms. We had the default boring hard NMS. So what this does is it loops through. Let me show you an image. What this does is when you actually run your DNN, it's going to give you a lot of I'll say extraneous bounding boxes. You see the one on the left in red. But what you want to do is you want to remove those extra boxes and get the one in green. So this is what NMS actually attempts to do. It's a heuristic to remove extra bounding boxes. It does it by a couple of methods, intersection of a union, merging the bounding boxes and whatnot. So here is the code actually in action. So this is our NMS code, and you can read more in the various papers. But I'll just let you guys know that we implement various heuristics as well. We have the default hard NMS and also a blending NMS, which I forgot which paper it was mentioned in, but this actually allows the bounding boxes to be more temporally coherent or invariant. So it deals with temporal coherence much better. So that's basically what we have. Okay, so that was the code sample. We have future plans for DOS. As you know, I showed you we're doing lots of work on robots. The stack we're writing, by the way, is generic. So it's not just centered on Spot. It actually works on any wheeled or legged robot. It's just that we have a specific driver for Spot right now. So we're moving beyond just legged robots. We're going to do real robots, drones, and submersibles. The same DOS stack can run on those as well. On the sensor payload end for SPOTON, for example, we're going to be adding more features. So we're adding pulse estimation. We're also going to add the ability to actually tell your breathe rate or your heart rate. So and also scene understanding. So there's a lot of more recent work in unsupervised and possibly reinforcement learning. And also, I think we might be holding a Spot hackathon, which we are encouraging everybody to take part in. So you should maybe pay attention to what we're doing, and then if you're interested, feel free to join as well. I think it's really exciting. So that's basically it. You can email us at this address, and thank you for attending the talk. Thank you so much.
Right. Thank you, Jia Yi, for the really exciting session, right? And also for sharing with us some insights on the great work that GovTech is currently doing on the digital operations smart services platform. So just to call out as well to all attendees, right? If there are any questions that you might have, please continue to post them on the Q&A section, and our speakers will also be hanging out at the same time, at the water cooler room in case you might want to interact with them. Right, so you have two avenues, right? You can actually check out the water cooler room to try to catch our speakers after the session, or you can also continue to post them in the live events Q&A, and we will respond to you accordingly.